in the same place. Okay, everyone. Good morning. My name is Peter Coveney from University College London. I'm one of the co-organisers of this meeting. It's great to see so many people here. It's obviously a bit of a hot topic. It might be hot as well in this place, and we have managed to get one window open. We couldn't open the other one, but I predict we may need to. In any case, as you all came through downstairs, that's the place where people register, and the refreshments are held, and you will have noticed stands for posters, and posters are already going up. I think at lunchtime there'll be a poster session, and we've got 12 or more of those. There's a competition there for the best end posters, where N might be 2 or 3. So toilets near the entrance when you come in, they're on this floor. Just go back towards the entrance on the left-hand side. A number of other points. This presentation and all presentations here are being live streamed, except people who didn't request that, and recorded and edited for subsequent purposes and posterity. As an introduction to this meeting, I want to say it's a joint meeting run by 2 EU Horizon 2020 Centres of Excellence in High Performance Computing. One is Computational Biomedicine, and the other one is BioXL. And we'll just have a quick couple of presentations by Bert from BioXL and myself, and then Bert will take over chairing the first session. I should tell you a little bit about Computational Biomedicine as a project. Just quickly, it's large. It's got 15 partners, but that's only the beginning in a sense. Those partners are distributed geographically across Europe, and they're diverse in terms of academic supercomputing centres, industries of various kinds, small, medium enterprises, and large-scale ones, plus activities involving clinical partners in hospitals. We have a kind of program for associate partners, and we already have more associate partners and core partners, and they're as diverse as the initial grouping, and they reflect the fact that a lot of people are interested in the sorts of things we're doing here, and our business is in the use of modelling and simulation, methods that are familiar in the physical sciences, engineering, applied mathematics, but sadly still bereft of a basis in many areas of life, and particularly medical sciences. So that's part of our mission in outreach terms. So for this project, for this workshop in particular, it will be rapidly evident to anyone who's just picking up how we do this work, or but familiar to those who do, that you can't take this area seriously if you don't have access to high-performance computing resources. These are centres of excellence in high-performance computing for the Commission, that has a big activity across the whole high-performance computing space, but we're interested in user-driven activities here. This particular project has access to a wide range of computational infrastructure supported by the partners and also by PRACE, which is the European supercomputing setup. We use some of their machines. Some of the machines we have access to are from associate partners, just not core partners, and even further beyond. Since this area is also of interest not just to academics, and the academics who are used to running jobs, perhaps the medics are not, but the mainstream academics running jobs on supercomputers with all the foibles and restrictions. If you're interested in this area from a company point of view, you have to ask yourself, where are you going to get those resources? Typically they're not available at scale on academic machines. Clouds are interesting. Cloud resources and partnerships are part of our own project, and things we do there designed to be deployed as easily on clouds as they are on high-performance computing machines. So outreach and dissemination. This activity could be billed as outreach and dissemination, as well as a state-of-the-art look at how you do free energy calculations across life sciences and medicine. Just to point out the usual things we're active on. Social media, we have Twitter accounts, LinkedIn, goodness knows what else, but we're particularly proud of the fact that we're going to run a big IMAX event at the London Science Museum on the 27th of September. That will be, the centrepiece of that will be a film that's been composited on the Mare Nostrum machine at BSc, and we'll have a whole bunch of simulations that are performed on supercomputers inside this particular project. And I think that's it from me. So Bert, would you like to take over?
Okay, yeah, thank you very much, and also a big thank you to Peter and the UCL team for hosting us here and playing a large part in making this happen. So it's great to see many of you here. I think it's also very appropriate to have a free energy meeting in a place called the Chandler House. Maybe a coincidence. Anyway, I'm here both as a free energy enthusiast and also as a BioXL representative. BioXL, as Peter already mentioned, is also a center of excellence. And the thing about BioXL is that it's centered at life science.
And we're there. Thank you very much for the opportunity to talk. Well, for the duration of my talk, you can sit in my place. And then we just do a shuffle afterwards. As long as there's one person here, it should work out. Thank you very much for the introduction. Thank you for the opportunity to show some things here. What I would like to talk about is approximating robust methods. So what we're trying to do is get faster methods to compute free energies, but not giving up the robustness of methods that are based in statistical mechanics. So the aim is to maintain the accuracy, but then we want to still use some speed up that we can learn from other methods. And I'll talk about two aspects there. I'll talk about a combination of methods that are typically seen as more approximate, but then we take the aspects that we like best of them and we combine them into one approach. And then I'll also talk a little bit about how we try to actually approximate a full thermodynamic integration curve from just a few simulations. So let me start with the first part. As I mentioned, there are methods that are typically considered to be more approximate in nature, maybe, and one of them that we've been working on for a lot already in the last couple of years is one-step perturbations, where we're basically simulating a non-physical reference state that shows overlap with some real end states, and we in one go try to calculate the free energy of going from our unphysical reference state to the real states. We do it in solution, we do it in ligand in a protein, and then you can predict ligand binding or relative binding free energies from those, basically. Now, what's the good things of this method? It's very efficient. You do only one simulation in principle, and the post-processing is recalculating a couple of atoms, so this goes very, very quickly, and it works very good, except if you do charges. So it works very nicely for small neutral groups. If you just do a methyl group somewhere, or you add a small neutral changes. It doesn't work so well for charged molecules. It doesn't work so well for things that have big dipoles. On the other hand, another approach of calculating free energies very efficiently is empirical end-state methods, where one of them is based on the linear response approximation, or LIE, for instance. And what you do there is you approximate the free energy by looking at the energy of the interaction energy, the electrostatic energies of your molecule and its surroundings. And then you would, in principle, if you want to do it correctly, you would need to simulate it in the state where it's charged and where it is neutral. Now, this works very well for electrostatics. That is derived also from it works in LIE or LRA approximations. People then tend to say, well, let's do the same for the van der Waals, and they approximate that as well. But that doesn't work so well. So what we see here is that we have two opposite methods that work well for different parts, basically. So that a couple of years ago already led us to suggest that we can maybe combine these approaches, where we say, well, what happens if we simulate an unphysical reference state? We use the one-step perturbation to calculate the free energy of going from my unphysical reference states to real molecules A, B, C, and up to Z. And then I use a linear response approximation to do the charging. That way I would only need to simulate basically these states that are drawn there. So instead of doing an alchemical process with a big change, where I'd have all these intermediate lambda steps, I would need much fewer simulations to do that. So the first time thing we did that on was a toy system. It was a bit of an increased buckyball with different functional groups here, and then we had 4 different molecules in it. I don't want to go too much into the details of that here. It's just that we had 16 complexes, so we compared this with thermodynamic integration to calculate the absolute binding free energy for these 16 different complexes. And you see exactly what I was just suggesting, basically, that the free energy of the cavity formation, so the non-polar part, works best. So this is the deviation with respect to the TI. This is the average deviation with respect to the TI data. The one-step perturbation works much better than an ad hoc linear response or LIE kind of approach. And for the charging, it's the opposite. I didn't even put the number for the one-step perturbation because it was really far off, but you can see it here also. It's for the complete thing, 122 kilojoules per mole off, so that's a big deviation. But that linear response approximation works much better with, in this case, 10 kilojoules per mole. It's a huge scale that I'm looking at here because I have charged particles. And in the end, you can get for these 16 complexes a correlation with the TI and our linear, in this case, linear interaction energies combined with the one-step perturbation that is quite decent. Now that was just a model system, so then we moved on to a more realistic case where we did it in trypsin. So we have a series of compounds that bind to trypsin, and we have just different functional groups here. And first we did them all with thermodynamic integration, so we do the free energy change between the molecules in solution and in the protein. First thing that we look at is whether we get cycle closure. So if you have these various arrows, they should add up to 0. Now this is within a couple of, or 1 or 1.5 kilojoules per mole basically, so that works quite nicely. And then we started to look at these individual aspects. And then the first thing that I want to mention here is this charging thing. So what we are doing here is we take the molecule, and the functional group that we're changing is actually completely neutral, and we're putting on the charges from this. And so we can do that with TI, and it always works very well because you get roughly a straight line, and you need only a few lambda points in principle. But you get roughly a straight line. You don't get exactly a straight line. So that's exactly what you would be doing if you're thinking of doing, if you parameterize your Hamiltonian like this. So you have Hamiltonian as a function of lambda that is just a linear combination of the neutral and the charged state. Then it turns out that your derivative with respect to lambda is the electrostatic ligand surrounding energies. So that's easy to get. And now if you actually try to do that with this LIE method, which is assuming that the neutral state we don't need to simulate, because we are only doing half the molecule, this works really badly here. So then you would approximate the red curve with the blue one, very bad. If you do linear response, where you would say I also simulate the neutral state, so that would be more appropriate, you get this straight line, because it's basically the average of these two. Beta is half, so you get the average of those two. That's basically the straight line. So you're getting there, but you're not really so precise yet. So then what we suggested, or this is actually being suggested in the late 90s already, where people were doing free energy extrapolation. We don't only know the derivative of the free energy with respect to lambda, but also its second derivative. And the second derivative, if you have this parameterization of the Hamiltonian, turns out to be just the fluctuations of this energy term. And in the 90s, when they tried this, the simulations were too short that these things didn't converge. But nowadays we can do, then you did 100 picoseconds maybe. Now we do a couple of nanoseconds, and these fluctuations actually converge as well. That means that we don't only know the point here, but we also know the slope of the DHC lambda curve already. So what we then do is we say, okay, we still simulate only the end states. We know where it should go through at the neutral and the charged state. We know the slope, and then we just fit a third order polynomial to those four data points basically that we can measure, and then we integrate that one. So we approximate the TI curve just from those two simulations by looking at the fluctuations and the values themselves. If we now combine this with the one-step perturbation approach, then you can see that our for the non-polar part, the one-step perturbation works very nicely as well. That's just comparing the TI to a TI again. And these are the deviations with respect to the TI. If you do the charging free energy, and you see this third power fitting indeed is much superior to the other more approximate methods. And then what you are getting from it, if you do the one-step perturbation with the third power fitting, you get deviations with respect to the TI that are a little bit bigger, but they're in the order of 3 kilojoules per mole, 4 kilojoules per mole for the total delta G. So that's a very quick estimate basically, because now here we did a simulation, total simulation time of 58 nanoseconds, and that would need to be compared to the 245 nanoseconds that we did for the TI basically, so that if you would do every step individually with the TI. You can even approximate this state. You don't really need to simulate this state. You can even approximate that one from this simulation as well. Then it speeds up a little bit more, but you also lose a little bit more in terms of the precision. Now we said we should do this in a more systematic way, basically. So this was one example. We were very happy that it works. And then we said, okay, we need to do this more systematically. So what we are now looking at is first for solvation free energy, and then we also do it in peptides of all the side chains. So we first take the small molecules, which is we take all the analogues of the side chain. So we cut them between C alpha and C beta, and we look at the solvation free energy of the small molecule that you end up with. And then we'll later on, but then the next stage we also do it in a small peptide, and then of course also in a protein. That's very nice because what you can then do, what you can then think of, is that you can get the free energy differences between all amino acids at a certain position. So you can basically do a computational saturation mutagenesis from just a few simulations. You would simulate the reference state, you would simulate the real molecules that you're anyway interested in, and you would be able to get the free energy differences between them in a robust way. So first the electrostatic part. Basically we see the same, just the way that we do it now is charged to neutral, so the curve looks the other way. But basically it's the same as we saw before. The TI doesn't give a completely straight line, but if we approximate it with the third power fitting, we get a very decent approximation. In some cases it doesn't go all the way to exactly the same slope. So for in this case for methanol, for serine in water, or the serine side chain in water, which is just methanol, we still have a bit of a deviation, but it's clear that the third power fitting is usually a better approximation. Then if we combine this again with the one-step perturbation, we need, of course, the amino acids are different sizes. So what is our reference state now? We tried two things. One where we just have a single soft core sphere. I didn't go too much into the detail of what we do there as a reference state yet. It's a soft core sphere. That means it is a particle that can sometimes have overlap with the surrounding atoms. So there's atoms that approach it, they bump into it in principle, there is a repulsion, but if they have enough energy, they can actually fly through. So we just use the soft core potential of the that people are using in free energy at the time. When we use two of those reference states, either one sphere, but then of course obviously something like an arginine side chain or tryptophan will not fit in it. So we also have a double sphere system, and then we align our molecules to it, and we actually sample a little bit their conformations within the sphere when we calculate the energies. That's more of a detail. Now the resolution is not very good, but what you see here is the comparison against the experimental solvation free energy. So we have experimental solvation free energies for our molecules, we have the calculated values, and then we can do this for TI, that's the blue circles, and we can do it with this OSP third power fitting method. The deviation from the line in the case of the TI is 1.5 kilojoules per mole, which is absolutely no surprise because this force field was parametrized to get these values, so this is just what we put in. But the agreement with the third power fitting, a more approximate method, is still very decent with 3 and 3.1 kilojoules per mole, and also with respect to each other, they're about 2.3 kilojoules per mole apart. I have here more compounds because I did not put in the charged ones there. Good, so then we wanted to do this also in a tripeptide. So as a first test of whether we can do this in a protein, so what we now have is this is our reference state. We put our soft core particle, this R atom, at a little distance with the dummy atom so that it actually samples a little bit more conformations. And what we do is we put in our real molecules, but the neutral ones, and we put in different conformations. So if we now want to calculate the free energy of in this case the arginine, we have first generated our own, according to our force field, a small conformational library, but you can also just take a Rothermer library in principle, and we put different conformations of this in the simulation afterwards. So we simulate the weird reference state. Afterwards, we put in these 5 conformations, calculate what the free energy for each of the conformations would be. We know the balance between the conformations from the Rothermer library, and we can combine that all into a free energy for the neutral state. And then we simulate this one and we simulate that one, and with the third power fitting we calculate the charging. So basically for one amino acid it's these 2 simulations and one reference state simulation for all of them together. That means that for 20 amino acids you're done with 41 simulations basically to get the free energies between all of them. Now how well does that work? So again here I compare to TI, so I have the TI data on the y-axis here, and on the x-axis our simulated data, and you see that that the correlation is really very good, 3.8 kilojoules per mole. So also when we need to take the conformational sampling of the side chains really into account, we can have quite a robust approximation of the molecules. There's here isoleucine. This is just a zoom. Isoleucine is still a bit challenging for that case. Now, so this was the first example that I wanted to show where we're trying to get the real free energies from just a few simulations and approximate them. So we are combining the strength of various efficient free energy methods. We have the non-polar contributions from the one-step perturbation and the electrostatic contributions from the end-state methods, basically. Now, the third power of fitting is a parameter-free approach, so that's nice. So things like LAE or LRA are often used by fitting the alpha-beta parameters. There's no empirical fitting necessary here. And it comes at no additional cost because we just include fluctuation data rather than only the average value of the energies. But, of course, there's no reason why the curve has to be a third-order polynomial. That's just given by the fact that then we have 4 unknowns and we have 4 knowns, basically, so we just do it. And then we were wondering if we cannot predict the TI curves directly. Can we not do this in a more elegant way, maybe completely? So what we're then trying to do, we're trying to look at the TI curve itself. So now I have a bit of a weird notation, but that's just, it becomes, later on it becomes internally clear. So what I use here is a big lambda for my reaction coordinate, and this is what we do in TI. We have our ensemble average at a given value of lambda, and we integrate over it. Yeah? So this is what we saw before. Now, if you start to do a simulation with TI, what you could do is you could just say, okay, I first simulate just 2 points, and then we get very similar as before. We get a straight line. Yeah? That's not a good approximation. Then we do 3 points. We get more of a curve already, 4 points, 5 points, 6 points. And then when we start to do 11 points, all of a sudden, at 11 points, we start seeing a peak. And with 21 points, we see more of a peak. So you always have to make sure that you don't miss the peaks, basically. If you start adding points to your simulation, did you miss the peaks? And what you need to have for the TI is a smooth curve that you want to integrate. So you would want to get something like this. So here we did 101 points. This is the solvation of methanol in water. And now what we were wondering is if we could not already predict the shape of the curve from just a few simulations in the beginning. So what we would want to have is that we could do 6 simulations. So we simulate a few. This would be a lousy prediction, basically, because integrating this red curve would be would not give us the correct answer. But can we, from the simulations that we have, predict already where the curve will be? So can we make the predictions from the simulations that we have to find out where these peaks are, and can we suggest where the curve is? Now, give it away already, we can. This is a predicted curve, so the green one is now the predicted curve from these 6 simulations that we can approximate the black curve basically from the simulations. Now, how do we do that? It's actually not super fancy or magical. The thing is that we need to predict what the derivatives will be at different lambda values. Now that's always difficult if you use soft core. So this typical shape that I now showed is one that you get if you do soft core. But we then just decided let's compute those on the fly, because that's not super expensive. This is not a very difficult thing to do. So what we're writing, our energy is 1 minus lambda can be to the power n. And now here I use different kinds of lambdas, one for the scaling and one for the softness. Doesn't really matter so much. But I just monitor this thing for the softness Lennard-Jones lambda, and I monitor it for state B for the softness Lennard-Jones. And in the derivative, I need a similar term, that these 2 terms are the same, but I also need their derivatives, basically. And now what we do during the simulation, we already calculate these sums for 101 lambda values. Yeah? So we just do that extra. Now that sounds very expensive because you do 101 energy calculations extra. But it doesn't cost you so much, because typically you have a simulation of 50,000 atoms and you're doing 10 perturbed atoms. You only need to do this for the perturbed atoms. So it's basically 100 times 10 atoms. That's 1,000, as if you have 1,000 atoms more. So you need to do a few calculations more, but we store these summed properties, and that allows us to reconstruct the energy and its derivative at any lambda point from the simulation. Then we're not there yet, because you still need to account for the fact that you have a different sampling, of course. So we just do the reweighting. So what we do is we construct the Hamiltonian at any predicted lambda value, and then we We get the energies, we get the derivatives, we do an umbrella sampling reweighting, and then we get to the true value, basically. Now, how does that work? This is the prediction from one simulation. From lambda 0, you get the red one. From lambda 1, you get the other one. If you would combine them, we can combine them with a linear weighting scheme. If you combine them, you already get a decent curve that looks actually not so bad, just from the 2 simulations at the end. And then we can do different kinds of predictions if we do that. So if we simulate it every 0.1, we get the red one, or you can actually not distinguish it from the real red one, from the real black one. But already the blue one, where you simulated basically 4 points, you get a very decent prediction of your full TI curve from just the 4 simulations that you did. Also here, in view of time, I will go very quickly through this one. Also here, we did it for this benzamidine case. Of course, in the protein, the sampling is a little bit more difficult, but still we can predict the black curve. It was our reference TI data from having 6 simulated values very decently. I have also some tables where I can show this in numbers, how well our curves deviate from each other, but I hope that you believe it just from how much the curves look like each other. So what are we doing? We're trying to reduce the number of unphysical simulations that we need to do, so the intermediate states of the thermodynamic integration, or get rid of them completely. If we do the one-step perturbation third power fitting approaches, then we're basically really focusing more on simulating our physical states. Or in the extended TI, we're using exact statistical mechanics to predict where the TI curve will be. Now, what are we doing this on? We're now applying this in true protein environments. And another teaser a bit is that the extended TI machinery we can also use to optimize actually the shape of the curve. You can do a few simulations, predict where the curve is, then you know where to simulate. That can be useful already. Or you can also predict if a different lambda parameterization would lead to a flatter curve. So you can actually predict already whether you can come up with a more efficient path to get a flatter curve, which is nicer to integrate. With that, I stop. I acknowledge some people, some group members, some funding and collaborators, and I thank you for your attention.
Thank you very much. I think we'll have one quick question.
I saw bar appearing on your last slide, but isn't bar the solution to all your problems? That takes all the higher derivatives. I don't understand why you're doing all this effort with the derivatives.
Yeah, so the thing is that indeed bar in principle, so this is very similar to bar, or the efficiency that we get is very similar to bar. Now you can say bar is the solution to all your problems. We still like to understand the curves and to see where you would want to focus your simulations. So that's still also something with bar that you don't know.
Well, that's the thing we have to look into. We should publish this work, but it's about the overlap of states. That's what.
Exactly. Then it's the overlap. It's either the curvature of the TI curve or it's the overlap of states. That's what the things that you would want to look at.
Okay. Yeah. Thanks very much again. So we move on to the next speaker, who is Berg Hess from Stockholm, and for those of you who were present yesterday, he already promised that if you have a good knowledge of the reaction coordinate, this is the solution for all your sampling problems.
Okay, so I would like to thank the organizers for inviting me to speak here. So I changed my presentation a bit after the discussions from yesterday. So for those of you who were yesterday, there was some interest in umbrella sampling and in other sampling methods. So I'll discuss those shortly. See if I can stay on time here. Okay, so I'll be speaking about a somewhat different topic, I think, than most speakers here who will be speaking about alchemical transition. So I will discuss reaction coordinate sampling here, and we're working towards optimal sampling. It's questionable if one can actually achieve the optimum, but I'll show you how we're working towards that. So most of this work has been done by my PhD student Chiefko Lindahl. As all of you will probably know, And molecular dynamics is a powerful tool, but it has problems with sampling rare events or transitions because the timescales you want to sample are often much longer than what you can achieve in molecular simulation. So here's one example. We were looking at the opening of a loop in an RNA system, and then if you would just run MD, you would only see one conformation, not the open one. So you would need to do something to actually see the other conformation, and for that you need to bias your simulation if you want to see that in reasonable time. So you need to add some reaction coordinate to make this work. And then you need some methods that actually allows you to drive the system over transition barriers. And that's one question is, what kind of method should we use? So I wanted to focus actually on a different topic here on optimization, but I think I need to discuss the method, especially after discussions we had yesterday. So the basic idea is that one can bias simulation. So if you do your normal simulation, you would get a Boltzmann distribution, which is this blue one, but I can add a bias to my simulation by changing the Hamiltonian in any way I like and get a different distribution out. So find something that's, for instance, flatter, which would likely allow easier sampling between these minima. And then once I have this, since I usually know what bias you've applied, you can unbias and get what you want back. So that's the basics here, which is rather simple. The question is then, how does one do this in practice conveniently and correctly? So a very short presentation of methods to do this. So there's an enormous zoo of methods out there, but I think the field is slowly converging towards the same kind of thing, which is good, I think. So the most well-known method is umbrella sampling, which is very simple and powerful. But the issues there, as I'll also show here, is that it slows down sampling by restraining your system. So you add an umbrella along your reaction coordinate and you sample different umbrella positions, but independently. So this leads to nice trivial parallelism, but since you fix your system along the reaction coordinate, it's not free to move back and forward anymore, and this will slow down transitions. The other issue there is that thing we've also been discussing yesterday, that it's difficult to move from the initially chosen pathway, so you need to set up initial structures to generate your starting states for the umbrellas. Once you've set that up, it's difficult to move these over barriers perpendicular to the pathway. So then there's a very popular class of methods, which is now referred to by metadynamics, but the ideas are much older. Local elevation or flooding by others in the field before it was picked up and popularized as metadynamics. So this has dynamic sampling along direction coordinates, which has strong advantages because you make use of the natural sampling of the system. But the disadvantage here of these methods is that there's no explicit target distribution. So you don't know what this distribution is that you're after. Maybe a posteriori you might know. So what I'll shortly describe now is the method we've been working on, which is called the accelerated wave histogram method, which is a very general method. There's nothing spectacularly new there, but this actually adds the thing that you have an explicit target distribution in there. So this is nice. So you have control. You can control what you want to get, but you can also check what you're getting, since if you're not sampling according to your target distribution, you have an issue. Okay, so the basic procedure is the same for all these kind of methods. I start out with some initial bias, which could be no bias at all, and then I run a bias simulation. I observe what I sample. Then from the samples, I estimate the real distribution, which is usually unknown. And then I can update the bias, so I can come up with a new bias based on that. And then with the new bias, run a bias simulation again, and then iterate until you're happy. So how do we do this with this AWH method? So this is the version we use is tailor-made for extended ensembles, where you add a reaction coordinate, which could be anything. It could be an alchemical parameter. That's not what we use it for. So we actually use it for reaction coordinates, which are generalized coordinates of the coordinates themselves, which adds complication. But and then the elements here is that we use an efficient update scheme to estimate the distribution and to update. And yeah, we explicitly include the target distribution as said. So I can't go into much details of the method here. I'll just quickly show how it works. So we initially had a scheme where we had molecular dynamics in your normal phase space, and then you have your reaction coordinate here is given vertically along lambda, where we do Monte Carlo sampling on lambda. So you have your umbrellas and you jump with them. So that's shown in the next slide here. So you could do umbrella sampling with individual runs, but here we jump with Monte Carlo between the umbrellas based on your target distribution and what you observe. Now we actually have a preferred way. We convolve the umbrellas to get a convolved potential, and then you can just do MD. So that's very similar to what metadynamics does with dumping Gaussians. So so we're pulling on the system, but not with a constant rate, and the system in the end, if the updates will be small, you're not pushing the system anymore, you go to equilibrium. Okay, so one important ingredient here is that we have an exponential linear weight decrease, which automatically tunes the time of the system. So you need to have some parameters in this method, not many, but one is by how much should I update? Like if you do metadynamics also, what should my update size be? So our trick here is that we initially had, in the initial phase, oh, I updated the slides, but I got the wrong one sent to Bert. Okay, so initially we have a constant update size, and then once we cover the whole range of the reaction coordinate, then we halve the update size. So that gives exponential decrease in update size. One can do this if when the errors is large. When the errors are larger than KT, one can be in this exponential kind of phase. But at some point, when we cross the diagonal here, where each sample has weight of 1, then we switch to a linear increase, as you would expect. So in the end, samples should count. The variance should go as 1 over the number of samples. You can't beat that. So the Wien-Landau scheme will go wrong at some point. But since we keep track of this crossing point, we automatically tune the update size for the timescales in the system here. So this gives us very, very quick convergence to errors of roughly KT, and then we get the normal, unavoidable convergence with the variance going as 1 over the number of samples, or 1 over time. Okay, so just to show you that this works, so this is a toy system. So there's basically only one critical parameter, so we can choose the umbrellas as tight as we want. That doesn't matter for the computational cost. So there's one parameter, which is the initial update size. So how much should I initially change my weights or my bias? So here I've shown this is the inverse size of the update, or it's the weight, and shown for many different, large range of values. And you see that they all converge roughly equally quickly to this regime of one variance goes 1 over m, except if my update size is very small. So if it's very small, then I just need a long time to fill up minima. So as long as you take it big, it's fine. You can take it very big and it works. So this is non-critical. Okay, so then actually show that this works on a realistic system. Ah, it's another, sorry. With this sending the slides to the back, a lot of stuff disappeared. Okay, so this is an example application here. So here we're looking at base pair flipping. So the reaction coordinate here is this hydrogen, this Watson-Crick hydrogen bond, and we want to see if bases flip out. So we just have one reaction coordinate, but there are 4 different moves can happen depending on which base goes where. So if you look at what the simulation actually does, so that's in this plot, you see that initially the system is pushed back and forward very quickly because we're updating the weights quickly, so the system is being forced around. And in the later regime, you get to actually diffusive motion if you get to small update size. So let's see with larger transition times. And then you get the free energy out, which is this black line, and the red is the convolved free energy with the umbrellas. So this shows that it works on quite complex systems. And this is, you need to sample more than these 50 nanoseconds here. So there's a few transitions, you can get some free energy, but the error is going to be relatively large. Okay, so but then what the point I actually wanted to make here is that we have our real distribution, we apply a bias, and we could, for instance, go to a flat target distribution. But the question is, should we actually sample a flat distribution? And that's just a choice we make, and that's a common choice. But I'll show you that it actually, the concept of flat is actually problematic by itself. So for instance, imagine you want to bias along a distance reaction coordinate. Then I can say, I use the distance as my reaction coordinate. Yeah, so that's the square root of dx dy dz squared. But I could also say I use the distance squared as my reaction coordinate. Equally valid, it's the same reaction coordinate, it's just a nonlinear transformation. But is a nonlinear transformation. If I sample flat in a distance, my distance squared distribution will not be flat, and the other way around. So flatness is not a conserved property on the nonlinear transformations of your reaction coordinates. So it's difficult to speak about flat per se. So what this means is that you need a metric to describe distances in your system. So what should you use for a metric? So we came up with this metric that's actually from a collaborator in our department, Jaak Lidmar, who had inspiration from this metric from Sivak and Crookes here. So what we're going to use as a metric is a friction tensor. So I look at, so this original metric proposed by Sivak and Crookes works for a fixed lambda value. So I have fixed lambda, then I can measure fluctuations in the force and complete the autocorrelation and integrate that. So that tells me how quickly do my force correlations decay. You can actually see that if you would do constraint pooling or umbrella pooling, this would actually be your error, divided by the total time then. We now have extended this to work for variable lambda, which has some complications which I don't have time to go into here. But this gives you a proper thermodynamic metric now, which involves dynamics, actually. So the idea is now that since we have a metric onto space, we can generate a uniform distribution with this metric. So that means that I set my target distribution as lambda as a square root of the determinant of this metric. So that's standard way of doing flat sampling here. So then the question is, does this actually work? So here's a very simple example. So here, just for testing, so here I look at the potential mean force between lithium and acetate in water. So I chose a very short region here. So here's the contact minimum of the two ions, and here's the solvent separator minimum, which is that state there. Whereas the water molecule, there's a barrier in between because there's one water molecule just doesn't fit in, or it's not so happy here. So then the reference run I did here with a constraint PMF, so I constrain this distance and compute the force. Well, I can also do this with a tighter umbrella, that would be basically the same kind of thing. So then I can compute this metric, which in the constraint case or the umbrella case would basically give you your error as a function of lambda here. So notice that this is a log scale here. So these errors the difference in error are very large. So here it's very easy to sample this in the minimum as well, but here in this middle point there's an issue because the water molecule and the hydrogen bonding network needs to switch between being a water molecule in between and not there. So this actually tells you something. The metric tells you that there's difficulties in the system here, so it's actually a useful indicator of what's problems in the system. But then if you look what happens if you use the AWH method, then the metric drops significantly. So notice this is a log scale, so this is about a factor, what is it, a factor 4 or so? 3, 4. So because you let your system free, the friction is much lower. So that's a nice advantage. And then you can see what kind of errors you get if you look at the convergence here. So this is if I would fully optimize my constraint or umbrella sampling run such that I have more points here or longer runs here and shorter here, I would get this red curve. Now if I do AWH, I get this green curve, which is a factor of, 2 or 3 improvement, which is roughly the same as the metric improvement. And then I can optimize, so this was flat, as to say, in the reaction coordinate, but now I can do flat according to the metric, which is the blue curve, and I get another improvement of about a factor 1.5. So this shows we actually get better sampling here. Now for a more challenging case, so this is again the DNA base pair flipping, so now I do it not in 1D but 2D, so the orange here is the original reaction coordinate, and then we have a misformed hydrogen bond here in a halfway open state. And we bias that as well, because this is a state which is stuck and is not biased very efficiently with the original reaction coordinate. So now we're doing it 2D to show that it's actually a proper metric in 2D. So we get a landscape with here the original reaction coordinate, here the extra one, we have 2 minima and a barrier in between. But this is the free energy landscape, so this just shows you what the free energy is. But if you look at the metric, it looks very different. So the metric has extreme high barrier here, which is somewhere on this edge of just before the saddle point, which is very high and very structured. So this by itself already gives you nice information of where the problems with sampling are in your system. So then again, I can do the same thing. So this is AWH, the unoptimized is the green curve, and the optimized is the blue curve. So I gain a factor 1.5 here. It's not so much, but it's free. I mean, computing this metric is not expensive. So, and you see that in the end they converge to this 1 over variance goes with 1 over time, as you would expect. Yeah. So conclusions here. So AWH is a robust enhanced sampling method without sensitive parameters. So I think that's actually one of the major, apart from that you want a correct method, it's very nice that there are no sensitive parameters in here. So you don't need to tweak around parameters, you don't need to think like how tight should my umbrella be, how many umbrellas should I have. And the initial update size, you can just have it as large as you want, and unless the system explodes, you're fine. It will decrease and things will work. So that's very nice. But a very large PS here, as I also discussed yesterday, the choice of reaction coordinates is still critical and hard. I mean, this method we think takes care of the sampling for you, but if your reaction coordinate is bad, you're still going to have issues, and that's the difficulty in all these cases. So in all applications we have, the major issue is coming up with good reaction coordinates. Now what helps a bit here is that one actually can look at this metric and see like, oh, there are issues here, and then you can look back in your system and see like, maybe there's an issue there and maybe I can improve my reaction coordinate. but the metric doesn't say how to do this. So this method should hopefully be released with GROMACS 2017 if it goes through code review. I can't decide that myself anymore. And so then, I think the more interesting part is this metric. So for bias sampling, you need a metric. I hope you convince you of that. And then this friction metric we think is a suitable and meaningful metric to use here. And sampling according to this metric improves your sampling. And it can be used to identify problematic regions. So this optimization we will not have in GROMACS 2017, but this metric will be shown, and it's actually been very useful in many projects to look at where you get peaks in the metric, and then one can look back at the system to see what kind of issues you have there. Okay, that's all. Thank you for your attention.
Okay, thank you very much. Any questions? I was actually wondering, I guess you mostly looked into cases where the barriers are enthalpic in nature, but I assume that this metric should also be useful in cases where you have entropic barriers.
Yeah, so this barrier here is mainly entropic, I would say. So this barrier is in low log scale. This is far higher than the enthalpic barrier. So this is to a large extent entropic because you have to. Well, yeah, the barrier here is not entropic, but you have a large change in states. Yeah, okay, so there's not. Yeah, but one it would also work for entropic barrier. So you would then you would see high metric peaks. So it's actually not here. And here are some entropic components, but yeah. So that's It's if you the other way around, so to say, if you would have a relatively flat EMF, you could throw out sampling issues because your states change a lot. That's not entropic per se.
Okay. So no further questions, and then we can stay in time and continue with Peter Coveney from UCL, and he will talk about free energy calculations.
All set. Thank you. Before beginning, I hope everyone's managing to survive here. The temperature, like in thermodynamics, we tend to generate more heat than light in our discussions, but the window is currently the widest I think we can get it. And the other one has been we've been thwarted in opening it so far. I opened that door, there's another one. So let's create more light than heat if possible. In any case, I want to talk to you about issues in the context of the relationship between thermodynamics and dynamics, or the microscopic world. There are very few talks in this meeting which use Monte Carlo methods. There's at least one. And if you're doing Monte Carlo, you know you've got a probability distribution and you pick things out of it. When we do molecular dynamics, people tend to think we're always at the molecular level and they pay lip service to the macroscopic. But these issues are very closely intertwined, and it pays us dividends to think a little bit about certain basic features of the relationship between dynamics and thermodynamics. Free energies are thermodynamic quantities, they're not microscopic quantities, yet we aspire to calculate them by using microscopic methods. Before I go any further, this is the sort of thing I'm liable to forget if I don't put it at the top of my talk, so I want to thank all the people who are listed in this slide, collaborators in a couple of companies, so I'll talk about some of the things we've been doing with them, and resources we use. Remember, I said at the beginning, we're in the business of high performance computing here. I can't do what I do now without access to resources at scale. Why? Because we want to do things in a hurry. Ultimately, we want to calculate things rapidly, accurately, precisely, and reproducibly, and the speed of which we do these things influences whether people pay any attention to us. At the sharp end of a clinical decision, I need to tell someone what action to take within hours or days. I have to have a method that's reliable, and then I'm in business, but I need scale at computing levels to do it. So quickly, that's what I'll talk about. I wanted to talk about the relationship between dynamical systems and ergodic theory, which is often used to justify how we compute properties at macroscopic level. So then the methods of binding for energy calculation, what we do to ensure they're reproducible, how we set these up so that they run in an automated way, so I can get answers in hours, not days or weeks. Okay, this is classical statistical mechanics. I don't have time to dwell on all the equations, they're standard. Most people write down Newton's equations of motion, which are the basis largely on which people solve molecular dynamics calculations. But I ask you to think of the probability distribution according to classical statistical mechanics. It's called ρ. It evolves according to the Liouville equation, and it has certain properties. You can make formal mathematical solutions of it using inverse Laplace transforms, but the main point I'm at here is, if I want an equilibrium state, I need to know the properties of this system at long times. If the system approaches a state that's independent of time, that's my definition of an equilibrium state. So the condition I need to have is, what does the dynamics need to fulfill such that the system approaches that state? And this is not new, but it's part of the subject of ergodic theory. And ergodic theory kind of parted company with people who do molecular dynamics 30 or 40 years ago. I don't often see these discussions in lectures or textbooks, but the requirement we need to get an equilibrium state is that the system is mixing in the hierarchy of dynamical systems theory. It doesn't need to be ergodic, and the next couple of slides will show you what the difference between a mixing system and a system that's only ergodic is, and there's a world of difference, but loosely, the system has to have these properties which make it unstable with respect to small changes in the initial conditions. This is at once profound. If I use philosophical language, it's of epistemological significance because it asks the question, what can I actually know of the behavior, even of a classical system that has thermodynamically interesting properties? And then what conditions I may need to draw from that, or consequences for doing these calculations. This is a pictorial representation, as it were, of the mathematics. And it simply says that if I have some uncertainty in my initial condition that's always used in a molecular dynamics situation, then if this system is going to have an equilibrium state, oh, by the way, it will do because we're measuring free energies. Then those trajectories diverge exponentially fast, and there's an intrinsic property of the system, the Lyapunov exponent, that tells you how fast it moves. It sounds practical, of no deep significance, but I assure you it is, and this is one of the reasons why people have turned the subject of ergodic theory into a mathematical approach, because to explore the consequences of any assumption you make on the initial conditions, you need to understand the limitations of a computer. People tell you that the universe is a computer, and I say to you, yes, but all the numbers that you use in a computer, the IEEE set of floating point numbers, has zero measure with respect to all the numbers that exist, most of them being irrational. You understand that your initial condition can only be an approximation because you're using a computer. And that approximation has the consequences, but the picture of what I'm getting at is represented here. If the system is non-ergodic, it just goes round in a circle. That little hatchet is the initial condition, the set of initial conditions I start with. If it's ergodic, it will wander through all the states compatible with the energy. But if it's a mixing system, it does much more interesting things. Pictorially, it goes to the state where this probability distribution is uniform. So the question about the relevance of the ergodic theorem is moot here because it applies to those systems, but not necessarily usefully or as helpfully as it could to systems that are mixing. And you would have to run a very long time to get this to work, yet it seems to be used often as the way of calculating properties. So what happens if you do multiple simulations? This is quite generic, actually. This is taken from work we've been doing over many years with the 9 FDA-approved HIV-1 protease drugs. You run the same simulation n times. That's the distribution of results you get. The distribution isn't uniformly scattered. It's rather like a Gaussian distribution. The question of exactly what the statistics are is still open, because anyone who does statistical mechanics knows the interesting systems are ones that don't have Gaussian distributions. But these ones tend to. So we're just showing you what happens if you run the same simulation, in fact, 50 times here. So this is the key to why reproducibility is such a problem when people publish results in molecular dynamics. One-off simulation doesn't have much value. I need to know much more about the system. And this is another picture taken from a recent paper based on a study of the peptide, complicated peptide epitopes are often called, bound to the major histocompatibility complex. And you will see what we did there to capture the statistics correctly. How long do you need to run the simulation? And as they say, read the paper to understand this, but 4 nanoseconds per run it 50 times, and you get the distribution, the ensemble distribution here. Run it for 1 microsecond, and you get that. So essentially, if you add up all the time you've taken, it's 4 times 50 nanoseconds is 200 nanoseconds versus a microsecond, and the results you get are much better. In fact, if you use 1 microsecond simulations here, you can't get a correlation with the binding affinity of the peptide with the MHC. You can if you use the right number of ensembles. So the problem often, in a characteristic form, is hope to run single MV simulations and then hope then to get some correlation between free energy and experiment. Of course, the experimentalists need to give us their errors, but it behoves us to produce errors as well. The situation we're in is one where we know one single simulation isn't enough. The other question is how many. And so from a statistical mechanical point of view, you could say, what's the number n of replicas I need, such that if I do one more, it doesn't change the result. And that's where we find what the numbers are that are necessary here. And typically, I'll just take you through what those numbers are, but if you do it nicely and it works out, you can get error bars of this sort. It's really similar to weather forecasting. The systems are different only in that we're solving Navier-Stokes equations, which are dissipative. In weather forecasting, here they're conservative dynamical systems. They still have the same chaotic properties. To know if it will rain tomorrow, we run ensembles of calculations with our Met offices. That's what tells me with probability X it will rain tomorrow. So then, to get down to the sort of meat and drink of what people care about when they do these calculations, this is an example of the sort of thing we're interested in. Using something like an MMPBSA technique, but trying to do it in a way where the results are obtained rapidly, accurately, if possible, precisely and reproducibly. And the main way of doing this as an endpoint method is to calculate one trajectory and assume there's no change when the molecule binds to the protein site. But if you want to relax that assumption and do 2 or 3 trajectory, then you have to do trajectories of the molecule in the solvent and the apoprotein as well. If you do all of those, and on a sizable computer you can then start asking what's the change, what we call the adaptation energy, when the molecule sits inside the protein. You couldn't do that with one simulation. It's hardly ever mentioned in most of the literature, and the reason is because the fluctuations are so huge. If you only do one calculation, the cancellation, as they say, of errors is so huge here, you won't get anything but noise. But if you do it in the way I'm advocating, you can get good correlation. So this is, how much time do I have there? 10 minutes. So this is the idea. Run a certain number of replicas, and there's no theory which would tell you how. It might depend to some extent on what your problem is. Here, for all the cases we studied, 25 is sufficient, but it's a dial. You can choose how big the error you'll have by cranking that up or turning it down. How long you run, so we can tell you what the error will be as a function of all these things. And it's much more efficient than trying to run these long simulations. It gives a reliable protocol, and then maybe this is aging, but when you find people reporting what happens when they do one simulation, in the light of the data we have, you can't take it seriously. But it's a function of computational power that we're capable of running so many simulations now. I keep saying 10 years or so ago, the largest computers might have only had a few hundred cores on them. Now they have hundreds of thousands. And whereas one was a heroic job previously, for some cases, it's utter chicken feed on a big computer. So then, how do you actually do these things in a hurry? That's related to computer science and sort of infrastructural issues, but we've invested quite a lot of time in developing something called a binding affinity calculator. It handles these type of calculations in an automated way, because you couldn't play this game if you tried to do all of these steps in a manual fashion. You build the replicas, you equilibrate them, you unleash production with your favorite molecular dynamics code. And by the way, I run the same code. It might be GROMACS on one platform, and I run the same code on another. I don't often get the same results because people change things, or even the same machine, there's some change in the software stack and things go wrong because of the instability of all this. But anyway, you can sort of see numbers here. How long does it take to do all the analysis? And it's a few hours, but I've used, let's say, of order 5,000 cores, and I get all of that done at once, and I can do it in an automated way. I think most people here are enjoy the subject of alchemy. Most people are talking about alchemical. That previous case wasn't, and it's interesting because it gives insights into a lot of information. That's why the endpoint are better, because we do waste a lot of time on these lambda calculations. It's good to try and minimize it. But I just want to tell you a little bit about our approach to those, because you see, thermodynamic integration succumbs to the same problem as these other things. They're molecular dynamics simulations. And this is just an example of what the rate of change of this V thing looks like with lambda when I run it a number of times. It contributes very heavily to the error in the calculation. But it's better to think of the molecular dynamics trajectory as something stochastic. It might sound hard because that's the challenge between determinism and free will. Surely classical mechanics says exactly what's going to happen, but I'm telling you it can never tell me precisely for the reasons I spoke about earlier. It's like throwing a dart into a board. What you get is something like a stochastic distribution. The statistics are Gaussian. And therefore this process could be treated as a stochastic process. That integral is to be thought of as a Gaussian stochastic integral. Every point on it is a stochastic process with some mean and average. And actually, from the theory of stochastic processes, I immediately know that the integral of a stochastic process is also a stochastic process, and it has a particular standard deviation associated with it. So there's a nice result. So that's how we do our thermodynamic integration, and it applies just as surely to all of these methods. The question for you is, how many times do you do this? Because these dials and knobs, you can choose to control the errors. And that's the workflow, how it maps onto the supercomputer that I'm using. At a superficial level, this looks nothing but the same as the ESMAPS thing. Those who are aficionados and love lambdas will see the difference, but we're just deploying all of them at once on the machine. And maybe for one calculation I need around 8,000 core hours. But I get the answer actually faster than I did for the other case, because there's less post-processing involved in this instance, and I have some error control. But you can use these methods with flexibility. We have designed a front end for this that enables us to deploy the application onto your infrastructure. It could be a local cluster, it could be a very large or set of high-performance computing resources, or it could be a cloud. So, because time will run out, how much more have I got?
4 minutes.
This is just sort of looking at the types of systems we've analysed with these methods. So the MMPBSA thing in the ESMAPS protocol is pretty versatile for many of the applications. There will always be issues here. Some of them are related to force fields, some of them are particularly challenging active sites with heavy metals, with charges on them and things, where people need to do better in terms of probably parameterizing. So, and there are different types of molecules. I mentioned using peptides, binding, small molecules, and trying to rank them. I would say the Esmax method is rapid, precise and reproducible. It's not accurate, but it's pretty good at ranking, with error bars of the order of 1 kilocal per mole or so. In the ties case, you can crank those down to less than a kilocal. You can get them down to 0.5 kilocals per mole. You can drive them down to 0.25. I'm looking at Brad in the audience, who knows about how much money a pharma company might save as it gets more control on the errors of these calculations. But it's a question here of how much you're prepared to pay, computationally as it were, and in time to get the answers out. Time is running out of the proverbial sandglass. Just quickly take in a look here, a nod at Sarah Skerritt, who used to be at Pfizer, and it's in the audience in a collaboration we did there, which was run blind on their set of track A pain inhibitors in a project that they have subsequently published the experimental work on. Our challenge was to look at their set of compounds and make predictions of them, and then they revealed what the results were to us. The basic thing here is that people like the Esmax method when it's done like this, precisely for the reason I gave earlier, that I get insights into this adaptation phenomenon. What's actually going on when the molecule goes into the active site? Is it a lock and key? Is it an induced fit? One or the other of that can give you insights into what step you might take next in a drug discovery context. And the story in this case is 3 trajectory is the best. There are instances for prediction where 1 trajectory works better, and that's because you're closer to a lock and key hypothesis. Ties for Pfizer, same sort of study here. For the cases where it's applicable, it works pretty well. And here's one in the but for the experimentalists. Many of the data sets we compare with don't carry even experimental errors on them, so it's hard to make a prediction where you have an error against an experiment which is a single point. So I'm very keen on experimentalists also putting their errors in, because it helps us to see how robust our own methods are. In another study of bromodomains, this was with GSK, similar sort of story. We did the same thing and looked at how we would predict with the ties and the Esmax cases. And actually, again, the story there is similar for those molecules, that the adaptation free energies, when included, make the correlation better, and they provide insights for the experimentalists who are involved in the project in thinking about design. Ties here is even better, where it's working and applicable. And the last thing I wanted to talk about here is going back to what happens when someone tells you they've done a simulation and they've reported 1 or even 2 repeats. How do I know what the errors are on the calculation? This one is a bit like what some people advocate, which is an n equals 1 in the sense of 1 trajectory simulation, but then subjecting the thing to replica exchange. So you can do what we call ties, that methodology where we actually run a set of replicas at each lambda value and perform replica exchange at each of those lambda windows. You can see this is recent work that's just come in while we were preparing for this conference from Agassiz in the front row there. What happens to the error as you increase the number of replicas, the number of times you do the whole thing, and it has a dramatic effect on that error bar. If you only do it once, the error bars are perhaps charitably of order a kilocal per mole. If you do it several times, it's of the order of 0.2 kilocals per mole. It's more expensive. Just imagine the Russian doll picture. We're doing alchemical. People don't like spending time doing all this computation between lambda equals 0 and lambda equals 1. We're doing it with a vengeance now. Replicas inside on the path and with replica exchange. But at increased expense, the error goes down in a systematic way. We can also drive it down by doing more replicas without doing replica exchange. So there would be problems if you pulled out the wrong higher temperature set. So the summary of my talk, drawing to a conclusion, is it's difficult to resist the reason why one should use ensembles in these calculations, because of the intrinsic instability of the dynamics of these systems. You can then try to do rapid, accurate, reliable, reproducible simulations, and the whole thing is intertwined. The fact that I do replicas gives me a handle on the error, and the fact that they're easily scalable outwards to large machines. Those machines are fatter now, they're not faster, the cores aren't getting any faster, there are just more of them. But since I can parallelize and scale out, I have an environment where I can compute till I'm blue in the face. We're lucky, we've just got an allocation on blue waters. This machine has 400,000 cores on it. It's replete with, those who love them, GPU accelerators, and about 128 million core hours to use in the next year or so. So we're not short of capability to run it here. So then you can start looking at these things in the context of prospective ligand design, and that's one of the areas we're particularly interested in. With that, I shall stop and thank you for your attention.
I think we can have one quick question before the next speaker sets up. Is actually David from Boise?
Yeah.
Yeah. Okay, please go ahead. Yeah, Derek.
So one concern is here when you're claiming that you're getting better, more accurate and more reproducible simulations by doing multiple simulations. Because as you mentioned earlier on, this is really about the sampling your phase space, right? So essentially what you're claiming is that by not running simulations so long, you're sampling less of your phase space. That will of course means that they're more correlated. You will get and because they're more correlated, the results are going to be more similar. But that's not obviously more accurate. It's more accurate if we have a free energy that doesn't really depend on sampling most of phase space. Which might be true in some cases, but it's not universally true.
Running a single long simulation is obviously not a sensible thing, since everything in it is correlated with what came before it. We know these systems.
I'll give you a very simple example. Assuming that you have a transition that takes 100 nanoseconds. If you don't simulate 100 nanoseconds, you will never see that transition.
Sure.
And if that was an important transition for the free energy, you're going to need at least 100
I
nanoseconds.
didn't claim that what I was doing here was a protocol that would apply without change to any system. This applies to the systems, as they say, to which it applies, which are relatively small systems for which we're close to equilibrium when we start. The initial condition in these simulations by classical mechanics will undergo some transient state, and it will end up in an equilibrium. If you've got multiple sort of minima and things, ultimately the whole system could be distributed across all of them. So you have to be very careful in picking the system in the first place. But one thing's for sure, run one simulation for as long as you want. It's not scientific. The next person who does it will get a different answer. And that is not
but the
scientific.
fact, the extreme is you can't do a billion one-step simulations. Because all simulations rely on sampling phase space, right? And the mere fact that results appear to be more similar to each other doesn't necessarily mean that they're better. They might be better if you didn't rely on sampling phase space, but it's not universally true.
There's a few things which are universally true, but one of them is that if you're trying to capture a property like free energy, you know the dynamics will have this instability property about it, which is why any single simulation will never capture.
No, I completely disagree with
that. That's wrong.
This is complete nonsense. If you sample long enough, the system is ergodic. It will
I
sample
just
all
mentioned
phase
to you
space.
that that's the problem of a Poincare recurrence, and it's not. And it will have to go through all the states compatible with the energy. That is,
and that works in
that's
most
the
cases.
Poincare
if you sample long
recurrence
enough.
theorem, and it will
In
take you
most systems,
longer than the age of the
Sample long enough.
universe to get to it.
Oh, come on.
It will take you
Yeah.
longer than the age of the universe to get to it.
We're talking about small systems. It's not going to take that long.
Yeah.
What's that?
We're talking about small systems. It won't take that long.
It's a small system. How small do you mean it is?
Well, you're the one doing it.
It looks like we're not going to exactly resolve this. So I suggest for the sake of time and
Yeah.
staying into the program, we continue.
Yes.
And we'll hear about the Schrödinger's look on free energies with the FFT plus.